Hi chemistry girls, this is my first attempt to make a little video and post it so you can hear me talking about some of the things that you're reading. We've got here a page, this is from chapter 17 in your book, and these are my notes so I can remember what I want to say to you. The goal of chapter 17, like it says in the introduction, is to learn how we can mathematically determine if a reaction, a chemical reaction, is spontaneous. We just see it on paper. We want to know if it's spontaneous, which means, as you can see over here in the notes, occurring by itself, sort of without human intervention, if you will. There's a few examples to help you think of processes that you're familiar with that are spontaneous. You can think about an ice cube that you set it out on the table or something like that, or you put it in the glass, and the ice cube will melt by itself, spontaneously. The example of rusting of iron, which again, even though it's not fast, it is spontaneous. You can also think about adding a drop of food coloring to a glass of water, and the food coloring will automatically disperse itself through the glass. That's a spontaneous process. In chemistry, if you think about the idea of a precipitate. If you mix together two solutions, and the precipitate will automatically form. There's a little disclaimer down here in the margin, and this is something that you also should think about, that sometimes if you're allowed to get the reaction started, but not continuously put in energy. So they use the example of a spark, or if we light the Bunsen burner, we use the match to get the process started, but then the burning of the methane gas continues on its own by itself spontaneously. Now as I said, we're trying to figure out if there's a way to look at a chemical reaction on paper and say, yes, that reaction will work, or no, that one won't work. As you read on, they'll tell you the ways in which that is determined. There's some familiar looking information here on this page, and like it says over here on my notes screen, how to determine if the reaction is spontaneous. First of all, we're going to consider the energy factor, endothermic versus exothermic. One of those kinds of reaction is more likely to be spontaneous than the other. You might be able to guess, but you can also read about it. So a consideration, the enthalpy change, the delta H of the reaction. Turns out that that's not the only thing that helps reactions become spontaneous or not. Down here they begin discussing something called the randomness factor. And just as a concept, randomness, they say, they use it in terms of probability. A low probability is a low randomness situation, or a high probability situation. The photo of the dice, we think about rolling a pair of dice, and the result of double sixes is a fairly low probability result. Chances are our dice roll will look something like one of these rolls here. You can also imagine a deck of cards. This is also used as an example sometimes. If you just were to pick up a deck of cards and turn them over and look at the cards, it would be very unusual to see that they were all organized by suit or organized in a numerical order, something like that. That would be a very low probability situation. High probability, the way we normally see them, where the cards are just randomly mixed up. So the idea of probability or randomness, we'll learn, also has something to do with a chemical reaction. Now, how do you apply the idea of randomness to science or to chemistry? You introduce the idea of entropy, which, as you can see here in the book, is measured with the letter S. I'm not sure why it's an S, but it's S for entropy. Entropy is actually a measure of disorder, or to tie it in with the words probability, like it says here in my notes, a low probability situation or a low probability substance we'll talk about is something that would be considered kind of orderly, neat, and tidy, whereas a high probability situation is one that's more randomized or messy. If you apply the word entropy instead, then you would be referring to the messiness or disorder. High entropy is a situation or a substance that's very randomized and messy, whereas low entropy means substances are very neat and organized. And the first discussion here is to discuss the idea of the entropy of substances. How much entropy do materials have? If you have an ice cube, or a balloon filled with gas, or a piece of metal, or a glass of water, the substance is considered to have entropy. It has a certain amount of disorder. So there's a discussion of that here in the book on page 454, and I think you'll find it pretty logical. But what we want to do mainly in chemistry is not only understand the entropy of substances, this is a high entropy substance or a low entropy substance, but we want to think about the idea of an entropy change. If some sort of a process takes place, are we viewing a situation where we go from a neat and organized situation to a messy situation? If so, that process is said to have a positive entropy change. It's a positive value. Overall, there's an increase in entropy. On the other hand, if this chemical reaction or the process we're thinking about takes us from kind of messy and disorganized stuff down to a neater and a more organized stuff, then that would be considered to be a negative entropy change. There's a decrease in entropy as you go from here to here. This is moving from low entropy materials to high entropy materials, and this is the opposite, moving from higher entropy materials down to lower entropy materials. And as you read through, they give you some examples of real-life processes and chemical reactions, both, that you're supposed to try and understand what's going on in terms of the entropy or the disorder. So some basic terms there that we want to know. The idea of a spontaneous process, which means it happens all by itself. We will understand how to mathematically calculate a spontaneous reaction. It will be a combination of understanding the enthalpy of changes of the reaction. That is it an endothermic or exothermic reaction? It'll also be a matter of understanding the entropy change in the reaction. Is it a positive increasing entropy situation, an increase in entropy, a positive delta S, or a negative delta S? So as you read the introductions here, you want to understand the concept of entropy itself, the amount of disorder in a situation or a substance. Materials have entropy, either high or low. A substance has entropy. Meanwhile, during a chemical reaction, there will be some sort of an entropy change.